Good morning everyone. Myself Dr. Assistant Professor, Department of Chemistry, Government First Grade College, Sirsi, Uttara Kannada. Karnataka State Higher Education Academy, Dharwad. Virtual Induction Training Program. Presentation on surface tension. Determination of surface tension of liquids by drop number and drop weight method. The presentation contains the contents or introduction to surface tension, adhesive and cohesive forces, why water has very high surface tension, examples for surface tension, determination of surface tension. Introduction. Surface tension is the tendency of fluid surfaces to shrink into the minimum surface area possible. Have you noticed when you fill a glass up to the brim with water, you can still add few more drops to it till it spills out? And or have you broken a thermometer and observed how the fallen mercury behaves? All these happen due to the surface tension of the surface. Let us understand the concept of surface tension, definition, along with the SI unit, formula, examples and determination of surface tension. Surface tension is a property of liquid, and as it appears by the name, this property is exhibited on the surface. Then what is surface? Surface is interface between liquid and another medium. Here that another medium may be a air or interface between two immiscible liquids. In the first figure, it represents the surface, that is interface between the liquid and the air. And in the second figure, the surface represents the interface between the two immiscible liquids. The surface of the liquid behaves like an elastic sheet. The elastic sheet-like property of the surface of liquid caused by intermolecular forces. Furthermore, there are two important terms which are related to the forces. First one, cohesive forces. Cohesive forces are the intermolecular forces which cause a tendency in liquid to resist separation. These attractive forces exist between the molecules of the same substance. While second one, that is adhesive forces. These adhesive forces are the attractive forces between the unlike molecules. They are caused by forces acting between the two substances, such as mechanical forces and electrostatic forces, that is attraction due to opposing charges. Let us consider the water which is filled in a beaker. In this beaker, water's adhesion to the glass is stronger than its cohesion to itself, creating the concave meniscus. And in the second case, what happened? The beaker contains mercury, and the shape of the mercury in the beaker is different from that of the water. See what happened here? Mercury's cohesion to itself is more stronger than the adhesion to the glass. That means it creates the convex meniscus. When the molecule very tightly. It's like a thin skin forms on the surface of the liquid. It's like a skin of the balloon. It's like a skin of the balloon, but it is much thinner. So that by observing all these points, surface tension can also be defined as the tension of the surface film of a liquid caused by the attraction of particles in the surface layer by the bulk of a liquid, which tends to minimize surface area. That figures shows the tensile force of the surface of liquid seen from the top of the liquid. So, this surface tension not only depends upon the forces of attraction between the particles within the liquid, but also on the forces of attraction of solid, liquid or gas in contact with it. The energy responsible for the phenomenon of surface tension may be thought of as approximately equivalent to the work or energy required to remove the surface layer of a molecules in unit area. As shown in the picture, a molecule located on the surface of a liquid lacks some neighboring molecules. What we are seeing, the surface, that surface lacks some neighboring molecules and thus experiences an imbalance of forces. Attractive forces of a molecule to its remaining neighbors are stronger on the surface of the liquid. As a result, a force develops that is directed at the interior of the medium. A water molecule deep within the liquid experiences a force of attraction by all its neighbors. Okay? Whatever the molecule which is present inside the bulk of the liquid, that experiences force of attraction by all its neighbors, so that net force is zero. Here in this case, the net force is zero. Whereas a water molecule at the surface, as I said earlier, lacks some neighboring water molecules towards the interface. So, the net force in this case is not zero. That is directed downwards here. Okay? In the first case, it is the net force is zero, whereas the molecules which are present on the surface, in such case, the net force is not zero. Okay? So, this unequal attraction causes the water at the air-water interface to act as a cohesive force surface, and the liquid to shrink into the smallest possible surface area. So, practically, the phenomenon is comparable to a thin layer surrounding the liquid and making it hard to dip an object in and to pull it out of the liquid. Against the force, work has to be performed to move something through this layer or to expand the surface. For this reason, the surface tension is defined as the amount of force that is in Newton per meter necessary to expand the surface in meter square of a liquid by 1 unit. So here, what causes the surface tension? That is what the question arises. Okay. See, intermolecular forces such as van der Waals forces drag the liquid particles together along the surface. The particles are pulled toward the rest of the liquid. So, surface tension here can also be defined as the ratio of surface force to the length L along which the force act. So, mathematically, this is represented as T is equal to F by L, where F is the force per unit length, L is the length in which force act, and T is the surface tension of the liquid. Coming to the unit of this, that is unit of this surface tension, we have 2 units here. That is SI unit, it is Newton per minute. Newton per meter, and in CGS unit it is dynes per centimeter. So the question arises now again, that is water in particular as a high surface tension. What property does water have that would give it such a strong surface tension? See, we know that cohesive forces between the molecules causes surface tension. The stronger the cohesive force, the stronger the surface tension. Cause of an electrostatic attraction between the hydrogen atom in one molecule. See the picture. One molecule and the oxygen atom in another molecule form bonds are called hydrogen bonds, which leads to strong cohesive forces between the water molecules, and surface tension of the water, for this reason it is very high. Okay. The surface tension of the water is very high because, as we know, here the electrostatic attraction between the hydrogen atom in one molecule and the oxygen atom in the another formed a bonds are called hydrogen bonds. These bonds lead to the strong cohesive forces. That's why the surface tension of water is very high. Coming to the examples, some typical examples for this surface tension. First one is walking on water. We have seen some of the insects can walk on the water surface. Here, water striders, which are small insects, can walk on the water as their weight is considerably less to penetrate the water surface. See the picture here, that insect, that is a water strider, can walk on the water. This is because of the surface tension of that water, and also the weight of the insect is considerably less to penetrate that water surface. And another important example, typical example for this surface tension is floating a needle. I think we have seen this in our home itself. This example is the best example for surface tension. That is, carefully placed a small needle can be made to float on the surface of water even though it is several times as dense as water. If the surface is agitated or it is disturbed to break up the surface tension, then the needle will quickly sink. This is another important example. Another example for the surface tension is shape of liquid droplets. Surface tension is responsible for the shape of liquid droplets. See the liquid droplets, shape of the liquid droplets. Although easily deformed, these droplets can be easily deformed. Droplets of water tend to pull into a spherical shape, tend to pull into a spherical shape by the cohesive forces of the surface layer. This is third example for the surface tension. Coming to the important aspect of this presentation, that is determination of surface tension of liquids by drop number method and drop weight methods. So many methods are there for the determination of this surface tension. In this session, we will discuss about the determination of surface tension of liquids by drop number method, and another one is by drop weight method. Let us see the first one. Determination of surface tension of liquids by drop number method. See, for this experiment we need some requirements, that is stalagmometer, specific gravity bottle, a small rubber tube with a screw pinch cap, distilled water and experimental liquid. What is the theory behind this method for the determination of surface tension of liquid is, in this drop number method, the number of drops formed by equal volume of two liquids is counted. If M1 and M2 are the masses of one drop of each of the liquid having densities D1 and D2. If N1 and N2 are the number of drops formed by volume V of the two liquids, then their surface tension are related as gamma 1 by gamma 2 is equal to D1 by D2, that is density of water and another liquid, into N2 by N1. Okay, that N1 and N2 are the number of drops of liquids and water. In this case, one of the liquid is water, its surface tension and density are known. Then the surface tension of the given liquid can be easily calculated. Before starting the experiment, let us know the different parts of the stalagmometer. That is what we are using in this experiment. Okay, stalagmometer basically a glass capillary tube, means glass tube containing a capillary inside, and in the middle there is a bulb. See there, this is stalagmometer, and this is the top of the stalagmometer. From this point, with the help of a rubber tube what we are attached here, we can set the liquid inside it, and this is the upper mark. Center is a bulb. Below the bulb there is a lower mark. It is represented as B. Above the mark, above the bulb, right? Above the bulb, that mark is represented as A. Inside this lower bulb, there is a capillary tube. Okay. Inside the lower bulb, there is a capillary tube, and the opening of the lower tube is very narrow, and there is a orifice through which liquid falls from the tube of stalagmometer in the form of a drop. So this is about the description of stalagmometer. To the procedure for this experiment. Initially, before starting the experiment, we need to clean that stalagmometer. So the first point in this procedure is clean the stalagmometer with chromic acid mixture. Then wash with alcohol and water and dry it. Next, attach a small piece of rubber tube, okay, what you have seen in the picture, rubber tube having a screw pinch cap at the upper end of the stalagmometer. Immerse the lower end of the stalagmometer in distilled water first and suck a water 1 to 2 centimeter above mark A. Mark A means above the bulb, what we have seen in the previous slide. Okay. Adjust the pinch cork so that 10 to 15 drops fall per minute. Okay, this is what initial adjustment. Then clamp the stalagmometer. Allow the water drops to fall and start counting the number of drops when the meniscus crosses the upper mark, that is upper mark is A here, and stop counting when the meniscus passes mark B. Okay, you have to start count the number when it passes a upper mark A and stop when that water passes the mark B, that is the lower meniscus. Okay. So next what we have to do is repeat the exercise to take 3 to 4 readings. Okay. And next we need to count the drops for liquid also. We have done this for water. That water is over. So for liquid, rinse the stalagmometer with alcohol and dry it. Suck the given liquid as we have done in the water case in the stalagmometer and count the drops as in case of water. Same procedure what we have seen in the water. Take a clean, dry weighing bottle, okay, that is a specific gravity bottle. Weigh it with water first as well as with liquid. And in this experiment, you should have to note the temperature of water that is taken in a beaker. Coming to the observation part of this experiment. The room temperature, what we have to note down is T degrees Celsius. Density of water, that is known, that is dW. Surface tension of water, that is gamma W, dynes per centimeter. Weight of empty specific gravity bottle is W1 gram. Weight of specific gravity bottle plus water, that is W2 gram. weight of empty specific gravity bottle plus liquid, that is W3 gram. Here weight of the water is given by W2 minus W1, that is weight of the specific gravity bottle plus water minus weight of the empty specific gravity bottle, that gives a weight of water. And weight of the liquid is given by weight of the empty specific gravity bottle plus liquid minus weight of the empty specific gravity bottle, that is W3 minus W1 gram. This tabular column shows the number of drops from a fixed volume for liquid and for water. So that from these three readings, we have to take a mean of the readings for liquid as well as the water. So for liquid it is NL and for water it is NW. So number of drops of water from A to B is NW. Number of drops of liquid from A to B is NL. Okay. So coming to the calculation part, it is quite easy. First we need to calculate the density of the liquid, that is dl. It is given by dl is equal to mass of the liquid by mass of equal volume of water into density of water. Density of water is known. So dl is equal to W3 minus W1 divided by W2 minus W1 into dW, that is density of water. Surface tension of liquid is equal to, that is gamma L, is given by dl by dW, that is density of liquid by density of water, into nW by nl, that is number of drops of water from A to B, that is nW, and number of drops of liquid from A to B, that is nl, into gamma W, that is surface tension of water, that is known one. So from this we can easily calculate the surface tension of liquid. So at the end we can easily report the surface tension of liquid in times per centimeter. Go to the next method for the determination of surface tension of liquid. That method is by drop weight method. Determination of surface tension of liquids by drop weight method. Here also the requirements for this experiment is again a stallometer, weighing bottle, a small rubber tube with a screw pinch cap, distilled water and experimental liquid. And in this experiment, the theory is the size of the drop of a liquid forming on a capillary head depends upon the surface tension of a liquid. The drop falls when the total surface, that is 2 pi r gamma, is equal to its weight, that is W. That is W is equal to m into G is equal to 2 pi r gamma. If the two liquids having surface tension, that is gamma 1 and gamma 2, are allowed to fall through the same capillary, then the relation will be like this: W1 by W2 is equal to M1 by M2 is equal to gamma 1 by gamma 2. Coming to the procedure for this experiments, this is also a very simple procedure as we have seen in the previous case. Again the same, that is clean the stallometer with chromic acid mixture, wash with water, then with alcohol and dry it. Second point, attach a small piece of rubber tube having a screw pinch cap at the upper end of the stallometer. Immerse the lower end of the stalagmometer in distilled water and suck the water 1 to 2 centimeter above the mark A, that is above the bulb. That mark is shown above the bulb. Adjust the pinch cock so that 10 to 15 drops for per minute. Next, clamp the stalagmometer and allow 10 drops of water to fall into the pre-weighed weighing bottle. Weigh the weighing bottle along with 10 drops of water. Repeat the experiment 3 to 4 times. This is for water. And for liquid, rinse the stalagmometer with given liquid, dry it with experimental liquid and repeat the above steps. That is the steps what we have did in the water. Coming to the observation part of this experiment, density of water, that is known, it is dW. Surface tension of water, this is also known, that is gamma W in dynes per centimeter. Weight of empty beaker, it is given by W1 gram. Weight of the empty beaker plus 10 drops of water, that is W2 gram. Weight of the empty beaker plus 10 drops of liquid, it is W3 gram. So weight of the liquid is given by W3 minus W1, that is weight of the empty beaker plus 10 drops of liquid minus weight of empty beaker. This is represented as M1. Weight of water, that is M2, is equal to weight of empty beaker plus 10 drops of water minus weight of empty beaker, that is W2 minus W1 gram. And this tabular column shows the weight of the drops of water and liquid. That is, we have taken 3 readings for each case, so that from these 3 readings we can easily find out the mean of the water as well as the liquid. For water it is W2 gram and for liquid it is W3 gram. Equation for drop weight method. Mg is equal to 2 pi r gamma. For liquid 1, M1g is equal to 2 pi r gamma 1. For liquid 2, M2g is equal to 2 pi r gamma 2. First one is equation number 1, second one is equation number 2. From these two equations, that is 1 and 2, it is given by gamma L divided by gamma W is equal to M1 by M2. Coming to the calculation part, surface tension of liquid can be calculated by using the equation gamma L is equal to M1 by M2 into gamma W, that is surface tension of water. So, by calculating surface tension of liquid, we can easily report the surface tension of liquid in dynes per centimeter. Thank you.